So I'll be going over problem 6 from the first problem set of David Tong's lecture notes. So I'll probably split this into 2 videos because it's kind of long and there's a lot of nuance. So we have this Lorentz transformation, and it's the infinitesimal version of the Lorentz transformation. So our lambda, if you remember from the last problem, we write it as just the identity plus our omega here. And so the inverse in this case will be I minus omega, which you can verify by multiplying these two things. So we need to know lambda inverse because we know our fields transform like this. And so we can just plug in our expression for lambda inverse, which will be this. And that will lead to our phi we can write our new phi as this usual expression. So our change, so this is, phi of x plus delta x will be phi of x plus the delta x dotted with the derivative of phi. So in this case, our change is just this. So we dot it with d mu phi. So we have this. Let's preview what's to come. So yes, we have this, and we need this because we're going to be calculating our conserved current. So we're going to need our delta phi's. So this will be our delta phi. And in this case, since we're changing the coordinates, we will also get a change to the Lagrangian, which will so the Lagrangian will transform in the same way. So we can just basically copy this expression down for the change in the Lagrangian. So everything is the same, just obviously phi is replaced with L. So, and then now we can just read off. So our delta phi here will be minus w mu nu x nu d mu phi. And our change in our Lagrangian will be the same thing, but with L. But we know that the term we get in our conserved currents, we need to write the change in the Lagrangian as the total derivative of something. Because so if the change in the Lagrangian is d mu f mu, then our current will have this term f mu. So we can't read off what f mu is just by looking at this. But we can basically pull this mu out, so it's basically integrating my parts here. Only I'm not integrating. I'm just I guess you can verify that this expression, so d mu of this. So in this expression, x obviously depends on x, and L depends on x. So I'll have a product rule. So one term will be the d mu acting on x nu, which is this term. So obviously that cancels. And then the other term will be minus, it'll be this term. And their d mu will be acting on L. So hopefully you can see this is equivalent to this. But this expression, so d mu x nu, is just delta mu nu. And that I can use that delta mu nu on this omega, so I can have omega mu mu. So I'll be summing over the diagonals of omega. But if you remember the forms of the omegas, basically the diagonals are all 0. So so omega mu mu will basically be the trace of omega, but since the diagonals are 0, this will be 0. So we can throw this term away, and we will just have this term left. which is good because I've written it as a total derivative, so we can identify this as our f mu. But I will play with the indices here. I'll introduce a delta mu sigma. So that's just with the benefit of hindsight. I'm going to do that. So this expression, obviously, delta mu sigma will act on this. It will give me w omega mu sigma, or mu nu. So this expression is just that. I've just introduced this delta function. So now I can write our conserved current here. It's because I have my delta phi and my f mu, which will just be this expression. So I'm not working with any particular Lagrangian here, so I just leave this term alone. But delta phi, in any case, if we're just dealing with the scalar field, will be just this term. And delta, or f mu, will just be this. So I'll just plug those in. But you can notice that both of these terms have a term omega nu sigma x sigma in common. So I can pull that out of both, and I'll be left with just dl d mu phi. Oh, you know what? I messed up just a little bit here because obviously I'm missing my d mu phi here. And then the only term left over in this is the delta mu nu L. And if you remember, this expression is just our usual expression for the energy momentum tensor. So this is T mu nu. So our conserved current becomes this. Okay, so this is our conserved current. So our conserved charge will be the integral of the time component of this. So just the integral of this when mu is set to 0, which is this. So I think I'm going to stop here. So we have this expression for our conserved current, our conserved charge. So we need to keep working with this. So basically, we know that there are 6 independent Lorentz transformations. There's 3 rotations and there's 3 boosts. So we should expect that really these 3 conserved charges, that this conserved charge can be written as the sum of 6 conserved charges that are each independently conserved. And so we'll see how that works out in the next video.